Good afternoon, everyone. I extend to you a very warm welcome to today's session. I sincerely hope that all of you are in the best of your health. I am Khwahish from Economic Times and your host for today's session. Today's panel discussion will be on the topic Improving Battery Performance with Multiphysics Simulation, organized by COMSOL and ET Auto. But before we get started, I would like to take a couple of minutes to set the context and then bring in our speaker to get the discussion rolling. Batteries are often the most expensive component in electric vehicles. One of the most popular choices for EVs, lithium-ion batteries are known for their high energy density, long life cycle, and low rate of self-discharge. However, a disadvantage of lithium-ion batteries is their sensitivity to changes in operating temperatures. For instance, an increase in temperature can lead to an increased rate of degradation and shorten the battery life. In today's session, we see how multiphysics simulation can be used to predict the thermal behavior of battery cells and packs, as well as to design optimized battery thermal management systems. And to enlighten us further on the topic, we have with us today Dr. Rustam Shekhar, Applications Engineer to COMSOL India. Welcome, gentlemen. And with this, I kindly request Dr. Rustam to take over and lead the discussion forward.
Thanks, Khwais. For today's session, what we are going to do today, we will go see how battery performs when we have different operating conditions, different scenarios, and in context, as Khwais said, the context that when we deploy those battery in the EV, and we see the different phenomena which may occur in the battery, and they may lead to some kind of degradation and some kind of failure. And if in general, if you operate the battery as well, then you will see how you can manage the battery without like you making it fail. To do that, we have to consider many phenomena or many features of batteries. All these things we will cover today in this particular presentation. So to do that, what I will do, I will just I want to ask you from from the audience to get a feel that how familiar they are with COMSOL. So what we'll do, we'll launch a poll to see how much people are familiar with COMSOL, which will help us to base the presentation. So can we have the poll for this? Thanks. So please register your responses. So this will help us to paste the presentation where we will get to know, okay, are you using COMSOL regularly, or you're attending a session for the personal interest, or you're just evaluating COMSOL for your ongoing project. So if you will be new to COMSOL, then we'll just paste a little slow, and then we'll tell you the all and each of the details which we have in our COMSOL. So please register responses, so we'll get to know, okay, what kind of audience that we are talking with. Okay, thanks. So I think you can see the poll results here. So most of the people are new to COMSOL, or they are just attending this out of their personal interest. So we will be elaborating the things on the basis of, okay, how they can, if they want to understand battery and the battery performance, how they can go for it. So let us close these responses, and then we'll go to more our presentation. So today presentation that we will cover that what is battery design module that we are talking about. And then once we talk about the chemistries which can be handled by this module, then you'll see how you can start with a cell level model and you can extend to the pack level model. So these are the two major areas where people work on when they are manufacture batteries. So they want to understand the performance and the design parameters for the battery. and later they will extend this extended study for the capacity loss or some kind of failure phenomena. So these levels, there will be a different level of fidelity to model the battery, which will be depends on the different data which are available. So in this so in the current scenario, people generally deal with or they struggle with the uh, problem the problem they face is the data requirement. So if so some people, if you are going to make a battery pack and you purchased a battery, then sometimes you feel the problem that your manufacturer don't provide you the data from the battery side, and that will makes the make difficult to make a battery model which is a very high fidelity model. Then there will be some methods to create a model which where we don't require the material data, and there will be you can create a battery model. And if you have battery data or material data, then you can go for a hybrid model. So there will be different fidelity level where you can work. And then once we come with a cell level model, then you can arrange them in a series of parallel, and then you can do your flow arrangement for the battery, cooling arrangement for the battery, and you can couple it with the battery management system. All those things you can perform, and then you can create your battery pack, which can be a pouch cell, cylindrical cell, or the prismatic cell. So all those sort of battery pack which you want to create, you can create by having any CAD or any design which you are having in your simulation. So and then once we have a battery pack model ready, then you can do some kind of thermal management analysis on that, which can be a flow analysis, and then this will affect your battery performance from the capacity side, or it can affect your performance side. And sometimes in extreme conditions, we see the internal short circuit or external short circuit, which leads to the thermal runaway. So these thermal runaway scenarios we generally seeing nowadays are very common, where people, where you are operating a vehicle in a certain operating condition, and they are catching fire, so which cause the hazards of the life. And then sometimes they create a doubt with regards to electrical vehicle. So we will address those issues by in this presentation. So let's just see what we have in the presentation. So when we talk about battery design module, then it is having some specific functionality to design a battery for the lithium battery, where we are solving for a detailed 3D Newman's model for a pouch cell or any kind of geometry, and you can work with the different chemistries which we say. So when we see COMSOL, so in COMSOL, what you do, you just compile different physics and come up with a module where you are accounting for a mass transport or concentration losses and the activation losses. So those different kind of losses you can account by combining all physics which contribute to those losses. So if you work with your mass transport, then mass transfer losses will you can encounter. If you operate at very high C rates, then you see your battery will offer more resistance, and your battery will get heat up. So those kind of scenarios we can have. So different physics which you want to compile and you want to solve, there you can have you can add all those physics, and this module will give you the functionality where you can add all those physics. So when we say, then there will be various studies that you can perform. So it can be a time dependent study, or the including transient effect, or it can be impedance study. So when you perform your experiment and then you want to compare a model which you built, or you want to validate with your experiment data, which because the validation is very important when you make a model, then you want to verify, okay, the model that you're working with is very accurate, or they're giving you right results. So to verify, you can create any kind of discharge curve or any kind of impedance plots as well. With this, then you can couple it with a different kind of multiphysics phenomena. So as name suggests with the console, that it's a multiphysics tool. So you can couple with different physics categories like fluid flow, structural mechanics, and heat transfer. And if you want to add some kind of stresses, and then you on the battery pack, you want to do some analysis like vibration or any kind of contact resistance, all those scenarios you can perform. So when we talk about the different chemistries which we can work with COMSOL, so first we have to understand, okay, how we deal or how we see a battery modeling. So there can be a different various levels or various fidelity that you can work on with the battery model. So it can be a very heterogeneous model where you are having all particles which are arranged in an electrode, and you want to analyze that electrode, how that will perform, and it will particle level, binders, and the electrolyte. So all your electrochemical and thermal profile you can map, and maybe you can monitor. So those models can be a fully 3D model where you have real structure of your battery. So let's say if you want to make a battery model and you are an experimentalist, so what you do, you have your scanned electron microscope images with you. So then if you want to work on the same exact geometry, so you can import those geometry, define, assign your physics, and then you can work with them. And then you will add the different physics like kinetics, mass transport, and the aging effects for the side reaction. So this particular model or category requires a material data. So which material you are using, then you have to feed in the material data and you will come up with a model. But when you work on a one level ahead and you want to go for only for a cell level model, you don't want to see what happens at electrode level, or you want to still capture the effect of the cell level model, electrode level model. Then what you do, we can homogenize this kind of scenario. So homogenize means then we assume that property earlier which was distributed, now they are having a average property with us. So those average property you will see, and then we'll give this average properties and we can make a model. So as you can see, there are in earlier model there was a particles was for the where you having lithium intercalation or lithium going to host inside the particle. But in homogeneous model you will not see those particles, but still you can solve for the intercalation. So those intercalation can be solved or will be solved in the extra dimension. So those extra dimension they will be there, and you can enable or disable this based on your operating conditions. And there can be one more model where you can go for one more simplification there, where we call them single particle model. So the single particle model can be used in a scenario where we have a low C rates. So on those low C rates, then we say, okay, I'm operating at a low C rate, so my transport losses won't be much, and we can have assumption that there are no transport losses. So this all three category where we started with a electrode level model to a cell level model with the different assumptions requires a material level data at the different levels. So when you require a material data and you don't have material data, then you get stuck in your model, because then you have to rely on some kind of approximation for the sources and all. Uh, then what solution that we got from the console, that what you can do, you can use the lump battery model or the 0D models or the this equivalent circuit models. Well, these two different models will still solve for the electrochemistry, but and then they don't require the material level data. So if you don't have material data, and if you know the capacity of your cell, and if you have a simple discharge curve with you, you can come with the same accuracy of level of model which we done with the heterogeneous model or the homogeneous model or the single particle model. So those level of accuracy you can get, but then it will deal as a cell as a whole. Then you will not differentiate between anode and cathode, and then you just see your cell as a whole. So if you want to go for the cell level model where you want to differentiate between anode, cathode, a separator, negative positive electrode, then we require a material data. And if your work is just to see the thermal analysis, capacity loss, thermal runaway, all those scenarios, and you are not designing your cell, then there will be very easy approach which will give you for same level of accuracy, which we call the lump cell parameter model. So they vary with the approach, and with the approach, then what you will see the different kind of computational resources also can make increase or decrease. So these are the approaches that you can take, and with a certain assumption or certain consideration. So they won't restrict you to only stick with the one kind of model or one kind of strategy. You will have a multiple strategy where you can approach your battery model. So now let's see. In this module, as we talked about, we can start with a electrode level model where you can arrange your all particles and you can have your structure with you. From there, you analyze your electrode, and then you can extend it to the cell level model. As you can see, it is a cylindrical cell, which is a jelly roll arrangement, and you can analyze this cell for the different layers. And later, we can transfer this data, or we can have a multiple cells arranged in a series parallel, and you can get the pack level model. So this flow that you can see right now is for the cylindrical cell. And now if you want to see for the same for the prismatic cell, so there can be they can be done for the prismatic cell as well. So which means it won't restrict you to design any battery which having a different geometries with you. So if you have any geometry, any series parallel connection, or any kind of structure or battery pack arrangement, you can perform your study starting from the electrode level to a cell level model or the pack level model. There you perform your thermal analysis and the other stuff. You can couple with the structural things, and you can do the structural analysis. and you can see the literally swelling of your battery. So if you want to see with a different operating condition whether your battery will get swell or not, then you can do that analysis as well, because we calculate the stresses generated in the battery. Okay, so now the journal functionality that we see when people want to know, as we know that there are people who are attending this out of their interest. So they should. So we just wanted to tell you that it will solve for first kinetics, which you can see, and there can be a very generalized form of the Butler-Volmer which governs the current generation, or else you can go for some simplification which we call TEFL, which can be anodic TEFL, cathodic TEFL, and some sort of approximation. And we can have the arbitrary temperature dependent kinetics. So when you change your temperature, your rate of the current generation will get changed. So this will be true for the side reactions as well. So we are accounting for all kinetics, which can be your main reaction, or it can be the side reaction as well. So when you do all those sort of stuff, then you are accounting and accommodating all phenomena which are happening or which are going on in the battery. So then later, when you took care of your kinetics, then you see the feasibility which take care by the thermodynamics, and you see the properties of the most battery where we have this Nernst equation which governs your potential. So if you want to see how potential is changing with concentration and all, and then you want to deploy your thermodynamics, then you can get your transport properties or the flow properties. And then now we have the feasibility and the rate with us, which is the current generation rate or the degradation rate. Then we can go for the electrochemical heating and deploy the anisotropic property, which will help us to design the cell or the battery pack. So then in this example model where we are seeing right now at the extreme right, these are jelly roll arrangement where we have an exact geometry of cell, and we are simulating this for the including all effect that we saw, so like kinetics, thermodynamics, and the electrochemical heating as well. So then now we're saying that we can handle any chemistry with this. So we can tell you that this is made for the specifically for the lithium battery. Some interface is specifically made for lithium battery because this is the current trend. So in this you can say which we will go through this when we go for the demo as well. So now right now you can see we have this different geometry built up with us. So it's a prismatic cell, you can see, and we have different electrolytes through different electrodes we have modeled, and we have coupled with the multiphysics, and we are solving for the all detailed equation that we can see. So we are solving for mass transport, we are correcting the properties for the structure. So we are accommodating structural properties, we are accommodating flow property, mass transfer property, and the charge transfer properties as well. And we are accounting for the intercalation and the reactions as well. And if you have some side reaction, you can add multiple reactions with this. So you can include the aging effect like SA formation, expansion, contraction by including the stress generated in the cell. So, and then this can be extended to the others chemistry as well. So when you have a solution, then you are not restricted only to the lithium battery. You can go for some electrode where we have a binary concentrated electrolyte, and you can see the hydrogen intercalating species. So you can define your different intercalating species, and you can work with any chemistry, as we say. So it won't restrict you only for the one solution, and you will get the multiple solution with that. So later part, if you want to work on the sodium ion batteries, then you can start your simulation or your studies straight away by using this module, and you can do the all stuff which we discussed for the lithium ion. So, and then you can go for solid state batteries and the liquid state batteries. All those things you can perform by using these interfaces. So, and then there are some trends that we can see. It is similar to the fuel cells. So we can see the flow batteries are emerging. So if you want to design your flow battery for your stationary operation or for the large scale operation, then you can go for the redox flow batteries as well in the system. And similarly, there is a very conventional one which we call lead acid batteries. So those lead acid batteries also you can design. So if you are a battery manufacturer, or if you're working on a battery, or even a student, then whichever study which is possible regarding batteries, you can perform. Either it can be very conventional one, which is lead acid battery, or it can be like current trends, which is lithium battery, and the intermediate steps as well. So you can define or decide all your battery chemistries, and you can analyze them as well. So, and then there are some unconventional batteries which people try, like lithium sulfur battery, nickel cadmium battery, or the zinc bromine, all those different chemistry which you can think of. So the logic remains same, where you know the physics and chemistry behind the battery, and you can literally model any battery chemistry by using this tool. So this tool will help you to design any kind of battery phenomena in the system. So now this leads to the second poll question, where we wanted to know on which area. So now right now till now we see, okay, what we can do with the batteries. Now which particular analysis you want to perform. So we wanted a response, so then we can will focus or we can stress on that particular part specifically. So please register your responses, so we'll get to know at what area you want to work on when you want to go for the battery studies. So we'll wait for some moment, and then we'll continue with our presentation. I think till then I can just take one question also. So is it possible to simulate cell swelling phenomena which is caused by the charging and discharging? So yes, you can model that, and for that you will get an inbuilt functionality where you are accounting for stresses during intercalation, and because of that, then you will see the phenomena which where you are having a swelling of a bed. So now we can see the results, as we see that people are entering in thermal part, where we have a thermal management or the thermal runaway, and other stuffs like capacity loss or the drive cycle analysis. So we can see here with this that thermal analysis is more important, which drive the all other phenomena like drive cycle, capacity fade, or the thermal runaway. So the other option that you showed, if you can type in that what other you want to try with the battery modeling, then you can have a discussion on that as well at the later part of the presentation. Let's see now what we have in battery analysis. So as we started with that, we can have a real structure of a cell, and we can create a model out of it. So those model, we call it heterogeneous model, because then there we are dealing with different phases like liquid phase, gas phase, and the solid phase. So those particles are in solid, and your electrolyte is present there as a liquid phase. So those heterogeneous kind of systems we can deal with when you want to go for the high fidelity model in the system. So this is a detailed model for the electrode side, where you are deciding the size and shape of electrode, porosity of electrode, which is a structural property. And then if you are not at the electrode level and you want to reduce your computational load, then you can go for the homogenization, where we homogenize the phase and we can come up with a slab, and that slab act as a model. So we have two approaches as we talked. Then there will be heterogeneous model and the homogeneous model, which capture the same level of details when we talk about. So now to understand the battery, let's just take an example or a study. With that, we will try to understand, okay, if you want to model a battery and you want to analyze the battery, then how they will help us to get the data or to interpret the simulation results. So we can set up a model, get a colorful plots, and those colorful plots we have to interpret. So those interpretation will help us to at what area we want to work on in the battery simulation. So what we'll do, we will take an example of an impedance plot. So in impedance plot, what we do, we will deploy a short perturbation in the voltage, and with the we will measure the current response of that. So that information will give us some details, and we will have details of like when we do the certain kind of parametric study, what they mean and how they can help us to optimize the battery performance. So the purpose will be we will investigate and perform the properties of a battery on an electrode, and small harmonic perturbation will be given, and the model can be from the 1D to 2D, any kind of level of model you can deploy. And in later part, if requires, then you can go for a parameter estimation as well. So when you get a battery and you perform your impedance plot on your real structure or real cell, and then if you want to extract the properties, then you can make use of parameter estimation and extract the properties as well, which are missing with you, or you want to estimate, or you want to go for the all properties. So we can see this heterogeneous lithium battery model. We have particles are arranged, and you can see in this animation that we can, with the time, with the discharge curve, how these stresses are getting generated, and the lead intercalation and lithium intercalation is happening in the battery cell. And another part, we can see the stresses and the intercalation part. So with the intercalation concentration, how concentration is changing, and with that, because of that, how my stress is getting changed. So we can get this impedance plot, and or else we can get the discharge curve. So both of them can be used to analyze the battery performance. So now, but when we come up to the one step homogenization, which we call the homogeneous model from the heterogeneous model, then we wanted to, so we want, when we homogenize it, so we have to make sure that if we do the homogenization, will we lose any detail or not? So then to do that, what we do, we compare both of the approaches. So in this model, you can see we have a 1D homogeneous model and a 3D heterogeneous model, and you want to compare the results. So in this, you can see if we are not ending up at a very extreme discharge in the battery cell, then we are having a very good match. That means we are going, we will go for the some kind of low discharge rates. So if you have if you don't have very high discharge rates, then you can just simply choose this homogeneous model, which is will give you very faster, and the results and models will be very light. Similar thing can be drawn from this Nyquist plot as well. So Nyquist plot, the tail of this Nyquist plot tells you that it's the difference in the tail. That means you can draw the conclusion that they are different, or they are having more resistance in the transport part. And then give me other board plot as well. So this is a comparison that we can make for the homogeneous and heterogeneous model, and we can safely assume that at low C rates, where we have a 30-70 kind of charge discharge, we can safely use this heterogeneous model or a homogeneous model to analyze the battery, and then later it can go for the battery pack. So there are some or more parameters which we can analyze. So let's say you just change the exchange current density, which is the rate of the reaction which you have in your cell. So when you change the rate of a reaction, then you can see at a higher rate of the current generation, you will have the less losses, which is this line. And when your reaction is slow, then you will have feel the more losses in the cell. So that means when we compare with the different rates of the equation, that means our rate is slow, and then we have to work on where my how I can improve my rates of the reaction. And similarly, if we will work with a different diffusivity, intercalation diffusivity, so the diffusivity won't affect the kinetics, it affects the transport part. So you can see at the transport part itself, it's showing some difference. So this way, by seeing this plot, you can decide at what area you want to work on for your battery performance. So in this, we can see we want to work on our kinetics part, and the other plot is saying that we have to work on the transport part. So the transport part, that then you can go for the size reduction, you can deal with a smaller particle, or the smaller particle will offer less resistance. So this way, you can decide at what area you want to work on. And some more results that you can see. So film resistance also will give you some information, and you can get the drive cycles and with some potential graphs. So all those phenomena you can couple, and then we can go for some 2D and 3D model, where we are having this pouch arrangement with the jelly roll. So you can see we can plot the one charge and discharge, and the negative and the positive electrodes, and intercalation and the de-intercalation. And you can see get this kind of discharge curve for the jelly roll arrangement, which is a 2D setup. And you can have a 3D setup as well. You can just extend this model to the 3D and get the similar results from the battery pack model. And then we talked about cylindrical. So now there's a prismatic cell, and a similar analysis you can perform on the cylindrical prismatic cell as well. So now we will see some kind of analysis. Now we made a model. We saw that how my model is performing with a certain condition. Now I want to see with some degradation phenomena how my battery performance will get affected, and how we lose the capacity fade. So as you can see, we will operate our cell at a 4 volt maximum voltage, and the lower voltage is 2.5, and we'll charge and discharge some certain ranges, and we'll run this cell for 3000 cycles. So for the 3000 cycle, we added a one side reaction, which is we called the SA formation, solid electrolyte interface formation. Because of that, we lose some material, so that material will cause the capacity loss. So then this capacity loss, you can see with the different cycles, and we go for the higher cycles, our discharge curve is getting shrink. So it will discharge faster. So earlier it was getting discharged up to 300 seconds, 3000 seconds. Now our battery is only lasting for the around 2600 seconds. So this way you are losing capacity, and you can analyze the results and result part. And the different battery capacity with the number of cycle, you can get the capacity plot as well. So we can see our capacity got reduced from the 100% capacity to the 90% capacity. So this helps us to the user or the person who is modeling the battery, or the manufacturer where they wanted to give the exact warranty to their customer. So when they will be able to predict the capacity with the with the using modeling, then they can go for some validation for their one or two experiments, and then they can provide the exact warranty to their customer. So there can be some mechanical degradation also we can include, as we discussed. So we can add the stresses part, and this plot I think we saw earlier also, where we have this with the concentration, and we can see how stresses are getting changed for my particles. So this relation we can maintain, we can create, and then as one of the attendee asked that we can extend it for the battery swelling as well. And you can see at a different time how my particle radius and the stresses are getting generated. So this will, or there can be multiple phenomena as well. So this lithium plating you see when you go for the higher C rate operations. So higher C rate operations, we'll see lithium will start depositing on the electrode surface, and this electrode surface will cause two kind of losses, where we can lose our capacity, and in worst case scenario, when lithium dendrite will touch the membrane or puncture the membrane, then it can cause us to the thermal runaway condition as well. It is short circuiting the cell. So till now we saw three different phenomena, where we have SA formation, we have this stress generation, and lithium plating. Similarly, if you have any other phenomena which you want to model, like gas evolution or any other phenomena, you can add and you can analyze your battery with a combined effect. So you can add the multiple side reactions and you can see the analysis. So as we talked that there's a model available, example model available, which talked about both. So it talk about the gas evolution in the positive electrode and the plating at the negative electrode. So both scenario you can model all together, and we will demonstrate you in the when we go for the demo session. So we can have multiple reactions, and you can go for the battery model. So and just internal short circuit, where you have want to simulate for nail penetration, which will sometimes your crash condition. So in a crash condition, you can see your nail penetration happened, or which can short the battery internally or externally. So the causes can be formation of dendrite, structural violence, and the manufacturer issue you can address with that. And if there is any vibration during the operation, any kind of resistance generated, so externally also your battery can short, your two interconnects or two bus bars may get touch in each other, or they may short the battery, or some wiring failure also can cause this kind of scenario. So now till now we just talked about the batteries. So now if we want to extend this model to the battery pack model, so we'll take all those interfaces, and we'll arrange them in a series in parallel, and we can come up with a battery model which will be thermally coupled, electrochemically coupled, and electrically coupled. So when we say electrically coupled, that means we are taking account of the all series parallel connection. So that will give you your real scenario, where you are having a series of battery which are in a pack, and then you are analyzing your battery for the capacity loss, thermal management, and the thermal runaway situation. So similarly, can be for the it's two different examples that we are taking, one for cylindrical cell, other for the prismatic cell, but you can make your any other geometries as well, which can be a pouch cell. Pouch cell also you can stack and make a model. So then once we have a battery model, battery pack model, what we do with that modeling? So we'll go for the heat generation account calculation, and those heat generation calculation will give us the exact cooling arrangement. So when you have a proper cooling, that it will prevent the SA formation or the gassing in your cell, or it will slow down the deterioration of the material. And in some cases, you can identify your hotspots, which can lead to the accelerated aging or the risk of thermal runaway. So when we understand what is my thermal profile for batteries, you can go for the cooling mechanisms, and you can prevent your battery from failing by aging or the thermal runaway. And if there's a scenario where you are operating at very low temperatures, like negative temperatures, then your battery may not behave properly. So then those startup simulation from the cold environment, you can do that. So these all are the transient simulation where you are cooling the battery, identifying hotspots for the real drive cycle or real structure. And in worst case scenario, they may cause the failure of the battery pack. So now the heat transfer mechanisms that we can deal with, like it can be conduction, convection, or the radiation. So if your battery is kept in an environment where you can see all three kind of mode of mass transport, and you can model and create a thermally coupled battery pack. So electrochemical heating, that we account that it can be Joule heating, it can be because of electrochemical reactions, heat of the mixing, and then we have the those element coupling to have a thermal management and the battery model. So then this will lead us to the last thing that we talked about, the capacity loss. We talked about the capacity loss. We talked about the capacity loss. We talked about the thermal management, and now we can talk about this kind of thermal runaway situation. So this performance has been performed, and this is a jelly roll arrangement which we made. And this jelly roll, we took a cell, and then we tried to simulate this for a single cell. And then we just what we did, we just performed a oven kind of test. So what we are doing here in that oven test, we just heating the battery, and because of the heating, external heating, we are observing whether my material will fail or we will get any kind of failure scenario or not. So analyze it. What we can do, we can have this kind of plot. So at a different oven temperature, you can see if you have a higher temperature, it will fail first, very fail, and it will then go up to 220 degrees Celsius. So this battery will get fail at when we have a surrounding temperatures 160. If we slowly reduce the temperature of oven, then we will not see those kind of failures. So this will give us the study where we have example that if you want to understand or study the failure mechanisms, you can do that. So this, and then this is a single cell model, and that can be performed for the battery pack. So where we will individually for the individual cell, we will track the concentration, and we'll introduce the short circuit conditions for the excessive heating. And so this example model that we'll show you, which will having the 24 cylindrical cell using the event heat resource to in a COMSOL multiphysics. When we design a battery pack, then you are, so once you understand the failure mechanism, then you can go for some mechanisms which you can deploy to reduce the failure in the battery. So this animation will tell you. So in this you can see we are having different heat sources getting triggered at a different time, and based on that we are having different temperature being generated. So this with the sequence, how propagation is happening in a battery or battery pack, you can analyze those kind of results. So I think then we can conclude this. So we talked about each and every phenomena which can happen in the battery or battery pack. Either it can be a thermal management, or it can be capacity loss, it can be a thermal runaway in the worst case scenario, and it can deal with all chemistry, all charge and shape of the cell. So it can be a supercapacitor as well, it can be flow batteries, and there are some degradation mechanisms for the cell. And we are dealing with very high fidelity model and some simplified model as well, based on the requirement of the user. So if you have any kind of problem or any doubt that you want to discuss, that then we can discuss. So for now, what we can do, we can go for a demo session. So in that demo, I will demonstrate you how you can simply create a battery model. Let me just change my screen. Okay. So I hope my console window, I changed the window, which is not a presentation. So I have changed to the presentation. I hope it's visible to everyone. So can someone confirm that my console window is visible to the audience? Okay. So okay. So then
Yes.
yeah, thanks. So we can now we can see the demo part of the console model. So what we can do, we can just tell you how you can approach us in battery modeling. So this is a console window where you can start your modeling, which field whether we have a model wizard and the blank model. In blank model, you directly reach to a modeling window where you can add your stuffs and start modeling. But if you want to go for all steps which are required for the battery, any kind of modeling, then you follow this model wizard. So in this model wizard, we'll go for model wizard. We can choose the dimension which we want to work on. So we can take a 3D model, and we can choose the interface which we want to use. So if we go to electrochemistry and this battery modeling, here we can see three interfaces are available for the lithium-ion battery, which is dedicated to the only lithium-ion batteries, and the other stuff which we talked about. So we can just go for a very high fidelity model, and we can add those interfaces. That means we chosen the what dimension we want to work on, and now we have chosen the what kind of study or what kind of physics I want to solve. So then it can ask you, okay, what kind of study you want to perform. So as we talked about, it's going to be stationary, time dependent, or the impedance plot. And in some scenario, you want to perform your cyclic voltammetry or the other stuff. So we just say time dependent. So we'll end up with a modeling window where we can define the other stuff as well. So first it will ask for the geometry. So what we can do, we can make a prismatic cell. So we can make a block, and in this block we can just change the height by 0.1 and say build selected. So this will be one layer of my cell, and we can add the multiple other layers as well. So we can say duplicate, and then we can add the electrolyte. So this is one electrode. Now we have one more layer, which is electrolyte or the separator, and we can add the other one as well. So you can say duplicate, and then we'll say build selected. So now we have all three layers available with us. And if you have other layers as well in the cell, like your current collectors and any other geometry, you can add that geometry as well, and you can work with that. So now we'll go for the material library, and we can add the material for the system. So we can say add material from library, and this will give you some material library data which will help you do all your modeling study. So we can see we have this electrode material available and some electrolyte material available. So you can choose any pair. Like I will take this graphite as one of the electrode, and I can choose the other electrode, which is a positive electrode. So I can take NMC, and then I can choose one of the electrolyte available with us. So this way I have added material, and then I can assign those materials to the different domain. So I can assign the different. So I can say this is my positive electrode, and this is my electrolyte, and then this is my negative electrode. So this way I have defined the properties, and I can add the different electrodes in the system. Video chalu hai. So we have this porous electrode, and the one more porous electrode, and we can add this separator as well. So now we can define our physics is in this. So if we go to porous electrode and say this is my porous electrode and the other one also, and so here we are defining the our structural property, electrochemical property, and some kind of degradation mechanism that we can have. So and then later we just go for multiphase coupling, and we can create our mesh to the system. So this mesh can be your define, or it can be phase control. And now you can run your cell model. So this will give you a very a flow where you can follow all steps, and you can come up with a battery model. So now what we can do, we can see a solve model where we can analyze the different kind of results which are available with us. So this is a model that we built by using the same interface, and the chemistry that we are having is graphite NCA and LiPF6, and this includes the degradation mechanisms which we call SA formation in the form of side reaction. You can see, as you can see here, and then we can plot the results. So once we plot the results, so the presentation you saw those results. So you can see this capacity loss with time and the discharge curve for the different cycles. So this kind of plots then you can perform. And if you want to go for further more studies and you want to analyze the electrode, then you can go for this kind of electrode model where you have same interface is being used, the battery interface, and you have the structure with you, dual electrode structure, and you can plot those kind of we can plot this kind of analysis where we have this concentration plot and the potential plot and the diffusion plot of my lithium. So this can be a full 3D model and can be a 2D model, and you can work with those kind of models. So let's just take one example when we add the heat transfer to it. So there's single cell model where we have two components. In one component, we are solving for my battery, and another component we are solving for the heat transfer and the flow. So when you want to do your thermal management, so you are assigning your flow and the heat transfer to the system. And when we solve these two models together, then you can see the temperature versus time profile and the load cycle as well. So this is giving you your electrochemical profile and as well as the thermal profile with the system. So you can see as the charge and discharge, your temperature is getting rise, and you have charging and discharging. And you can see the temperature and the flow pattern of around the battery, which is a natural convection which we are making. Okay, so now we can so these are the models that we generally build. And now what one interesting thing that you can do where users are not very well versed in electrochemistry, but they're in the organization, people know how to model a system. Then that user who know the modeling part, then they can create a app kind of scenario. So a very app kind of interface where you can see these interfaces are having some details, but you want to create a very customized kind of interface, then you can go for this kind of interface where we just customized it for the usability, and by using drop down menu you can just choose and you can update design, and simply you can just analyze your systems. So this is a part where we are modeling the system, and then we're creating a customized interfaces for my analysis part. So this can be helpful or useful when you want to work with a team which is an interdisciplinary team. So in an interdisciplinary team, you want contribution from the various fields, and to get the contribution, you can just share this apps to the user, and by using the drop-down menu, they don't need to do much in this model, and simply they can see the results part of it. A similar kind of apps can be created for any kind of model. So let's just take, if you want to design a battery, then what kind of app that you can create. So this is a very highly customized app which you can create for your analysis as well. So as you can see, we can choose the type of cell. So it can be cylindrical, prismatic, pouch, and size and shape. And in the cell, then we can decide the material which you want to use. And then we can define the thermal condition and loading condition, and later we can just simulate it for the different operating conditions. So here we can see the results and some plots as well. So this drop down menu you can create, and you can see the heat sources from the battery model, and cell voltage and loading, and you can create. I think you can create this entire interface for your application, which will be customizable for your application. So I think this is all from my side for the presentation. So now we can just start taking up the questions which we have. So let's just start from the top. So the first question is, which tool is used typically for this kind of simulation? So COMSOL Multiphysics is a tool where we are using COMSOL Multiphysics and doing all these kind of steps. And there's one more query that how I have to design a battery cell in 3D model software means, can we have a design anode, cathode, and separated differently? So it's up to you that what detail you want to have. And if you want to design those 3 layers in a 3D, then you can do that. And if you want to get rid of that and you don't want to go in that level of detail and just interested in the cell performance, then you can do that as well. So it's not required to always go for all 3 layers, and you can just skip that part and just go and get the overall cell performance, which also high fidelity electrochemical models for you. So there is one more question. Can I get this tool for a month? If found it useful, then I can go for purchase. So for this business part, you can write us to the console at support@console.com, or you can get in touch with our team so they can help you, I think, with this part. So there is a question that does COMSOL has any booklet documentation for physics use? So yes, so for each and every module, we create documentation, we maintain documentation where you can see the theory, equation used, and the technical reasons to observation of battery. So I think that COMSOL window itself also having that kind of system. So what you do in your interface, you can see the equations which we are solving. So if you want to see the equation solved for the electrolyte, so you can see in this equation section, you can see the equation, and if you want to add it or added those equations, then you can edit those as well. So all those equations are here in the tabulated form. So in this tabulated form, you can change all those settings, and if you want to modify one of the equation, you can do that, and you can work with that. Okay, so is it possible to measure the degrade value of using battery? So I think you are interested in the capacity loss. So yes, as we demonstrated, you can perform your capacity loss or degradation by using these modeling studies. And you kind of the one query where we say durability with thermal blasting can be undergone. So yeah, so you can perform your failure scenarios, and in those failure scenarios, then you can get to know, okay, what will be the maximum temperature, what will be the temperature profile, electrochemical profile. So you can see the, okay, what will be the thermal profile of the system, and which will be similar to your blasting kind of behavior. So this durability test with this, from the structural side and electrochemical side, you can perform and you can see the results. Okay, so there is one more query. So which cell structure gives max efficiency? So it depends that if you want to ask me, then all cells are generally there's the three layers which are rolled together. So generally they are the planar cell, and they just arranged in different manner for different kind of heat arrangements. So efficiency wise, you can do the analysis and you can compare different models, and then you can get to know by yourself. So if you want to try it out, then you can just let us know. That's a question that can we get a presentation, so I'm not much aware of it. For that, I think you can write to us, so we can just have a chat with you. There's a query that can you please touch upon the battery cooling system for the cylindrical cell arranged in a series in cooling plate or one of the end. So yeah, so this is a very common phenomena, a very common practice now people are doing. What they're doing, they're having a plate, on that they arrange their cells, and then this plate they are having this cooling arrangement. So as we showed you the demo for this battery pack, here you can do that. You can have one more plate just below to this structure, and you can do see the how that battery is being cooled and getting optimized for your structure. So yes, you can add the geometry, you can make the geometry for your battery pack, and then you can do this analysis. So what are the reasons of 2-watt EV battery fire? What are the prevention method in the design as well as testing? So it not specifically for the 2-watt EV batteries. This phenomena can occur at the any battery which depends on the different operating conditions. So we have to understand how this battery is getting failed. Then once we know why this battery is getting failed, or battery pack is getting failed, then we can go for different mechanisms or methods. It can be liquid cooled, can be phase change material, it can be a proper cooling system for the battery pack. So all those or thermal padding. So all those sort of design things we can perform once we know, so we can deploy this very efficiently. So it's a query that can we interface the power electronics converter to the battery to the console to see the battery performance. So that's when you say power electronics, that means you are talking about the battery management system, BMS. So for that, I think we have the labeling with Simulink. So in the Simulink, you can design your feedback loop, and on the Simulink, you can analyze, you can import entire console model, and do this kind of electronic converter kind of studies for the power electronics. Let's just take to one or two more questions. Are there abundant material property available for the various thermal conductivity adhesive which can be used during coupled simulation for the? So as I showed you some of the material property which are available with us. So all those very state-of-the-art material library is available with us. So we can take those material properties and start doing a simulation. So there is a approximation. So there's a query that approximation percentage deviation heterogeneous model and the lump model. So if you compare your heterogeneous model and the lump battery model, then they won't be much different from each other, because the parameters which we estimate for the lump battery model will drawn from the heterogeneous model. So heterogeneous models can be converted to the lump battery model. So then there will be no difference, no deviation, and can get the match based on your how you are estimating your parameters. So the percentage error which you can allow in your parameter estimation, that is the only deviation that you can get. If you have a tight tolerance for you, then you can go for the very exact match in case of heterogeneous model and lump battery model. So I think there is other sort of questions also available. So there are lots of questions. So we can take one or two, and then we can pass on the dice to the quiz at the end. So the question that disadvantage of owning a electrical vehicle, the range of electric car depends on that battery range is important consideration. How to overcome these issues? However, this holds true for the diesel and petrol cars as well, with the only difference being that their range is depend upon the age and the performance at the internal combustion engine instead of battery. So when you are worried about the range of your battery, that means what happens in a car electric vehicle, if you have a battery with you and your motor with you, so both need to be cooled. And to drive those cooling system as well, you required power. So that power also come from the battery pack itself. So this is a very coupled phenomena. So when you design so right now the battery pack which we use in India, they are oversized. So when you size your battery accurately, then this range anxiety kind of thing can go off. And if you have proper or frequent charging stations, then you can. There is no problem by using the electrical vehicle when you like a petrol pump. If you get a petrol pump at every 5 or 10 kilometers, so that will resolve the range anxiety which we work with. So. So I think we can just now pass. So we have a lot of queries, so which we can address and we can reply by our support portal, where we just individually email you with the answers of your queries. So and we can just if you require, then we can have a call and discussion with you as well when you want to go for this kind of discussions. So then I think I can pass on the dice to the quiz, and then we can conclude the session.
Thank you, Dr. Rustam, for such an insightful session. We gathered quite some interesting learnings from the presentation. But before we wrap up, I would request our team to please put the next poll. We come to the end of today's webinar. Thank you, Dr. Rustam, once again for taking out time and being with us today. I hope you found this event insightful and engaging as much as we enjoyed putting it all together. Before we wrap up, Team Economic Times wishes all our audiences safety and the best of health. Have a great evening ahead.